I'm Peter Love. I'm a professor in the physics department at Tufts University, and I work on quantum computing, mainly simulation of quantum systems using future quantum computers. And we also work with today's noisy quantum computers.
Do you work on a theoretical level or also?
Yeah, so I'm a theoretical physicist, but we also do, now you can access quantum computers through the cloud. So even as a theoretical physicist, you can actually run things on machines remotely. So we do that, and we also work closely with our experimental colleagues to try to do things on existing quantum computers.
Your own idea about quantum computing and encryption today?
Well, so the things that I work on, I usually think about them as applications of quantum computers that you would be able to use before the quantum computers became large enough and powerful enough to address cryptographic problems. So that's, I think, one of the reasons I like those problems is that, firstly, they're probably some of the earlier applications. And secondly, you can imagine having a device that would be quite powerful for doing quantum simulation, but you wouldn't have to worry that it would be some kind of threat to encryption or to, things of that nature. So, 1,000 qubits would be very nice. Now, with the latest results on Shor's algorithm and implementing Shor's algorithm, that might be a 2,000-bit RSA and thing, so maybe key. So maybe that would be something you might want to worry about. But nevertheless, I think the applications I think about come before we get to cryptographic things. But these are moving targets because people are working to refine the algorithms and to improve the implementations. And of course, the hardware is moving forward. But we're still, from applications at that scale, at the sort of thousands of qubits scale, where you're talking about millions of physical qubits, we're still quite a way away from that. And so I think we have time to see how things are going. So it doesn't keep me up at night. But I would also say, I think if people are still using RSA, they should stop because, you should be prudent about cryptographic systems. You shouldn't just assume, it'll probably be okay. I know NIST has worked a lot on post-quantum cryptography and establishing post-quantum standards, and, people should adopt those.
Well, we actually have this question for everyone. So what is your expectation?
I think it's very difficult to predict. And I think it's always been hard to predict how quickly things are going to move. And in the past, people would worry about being too optimistic and saying I many times have said, in 5 years, we will see X. And 5 years later, we have not seen X. So now, I sometimes feel like we have the opposite problem, that, in 2020, we were really starting to think about error correction. And if you'd asked me in 2020, when will we first see the first error-corrected qubit, I would not have said 2024. And that's when we saw the first error-corrected qubit in multiple realizations. And so now I think it's hard to predict because things can move faster than you would expect. So that makes it hard to say. I'm not answering your question in a long-winded way, sorry. But, I think if you look at the roadmaps that Google and IBM have, they're thinking seriously about getting to devices that have thousands of physical qubits. And the next thing along the way is sort of 100, maybe 100 logical qubits. So if you had 100 logical qubits with the new encodings, you might be able to encode like a 120. I mean, I think you can certainly do a 128-bit key. So when would you have used a 128-bit key? We can probably remember using one. Right? Yeah. Right. So that's not a threatening thing, but that that you might see that in the next sort of 5 to 10 years. And I think that would be very useful because if we could really get there with smaller keys, then you would have more of an understanding about what's involved. So it becomes more predictable what's the engineering pathway going to be. So I think the next 10 years are going to be very exciting for everybody. And we're now coming to the end of this, what we call the NISQ era, this noisy intermediate scale quantum era. And what's the next thing? The thing that comes after this is we have one logical qubit, one encoded qubit. Well, when are we going to have enough encoded qubits we can do something interesting? And so then John Preskill actually coined this idea of a mega QOP machine, 1 million quantum operations on about 100-ish qubits. That sort of seems like a very sensible next thing to try to achieve.
And meanwhile, though, there could be another breakthrough or other discovery where we don't need that amount of qubits. Maybe we need less. Actually, you suggested this paper that was out the other day. Actually, I think it's circulating. With 1 qubit, they can. Is it one? Right?
It was three oscillators, 1 qubit, and the energy of several stars. but we like the paper.
Yes.
The paper is solid because it shows how to shift. You shift the problem here from there, and this is a really good exploration.
Yeah. So I mean, things like that where you really understand how far you can trade one kind of resource for another or one thing, and then there's kind of optimizations and learning to do things more cleverly. So Craig Gidney has this paper from Google that came out in May, the third week in May, and there they went. It's like a 20 times improvement, as I understand it, in the number of qubits, but they do considerably more operations to factor integers using that method. So yeah, there's a worry about whether we could suddenly see a change, and all of a sudden you can factor integers much, much better.
Yeah.
Well, if you really want to stay up at night, you should worry about number theory, because you have to remember that there's no theorem that says that factoring is classically hard. So, in fact, it's entirely possible that factoring is not classically hard. Now, almost nobody believes that that's true. And people who do believe it, it's not clear if they say that because they want to stimulate people to think more about number theory or because they really believe it. But in that sense, RSA is not an absolutely secure system in the first place. So yeah, you're always vulnerable to sudden breakthroughs. But the more people have thought about the problem and the longer they think about it, the less and less likely, a sudden breakthrough. Then you're in the realm of paranoia, which obviously cryptographers live with, and it's an important part of it. Or just really magical thinking that tomorrow I'm going to have the most amazing idea and we're going to break everything down. Yeah, so I think the more we work on it, the more we understand how hard the problem is, and the less risk of that there is. But as I say, if you're using RSA, I think you should stop.
Yeah, I am actually having an interview with Ron Rivest in a week. And I already wrote him, well, the RSA is dead. And I don't know if he's going to agree. Factoring of two numbers, one-way function, could be just a mathematical assumption, so we don't actually know. And do you think studying quantum computing or physics might reveal something about that, like a new form of math?
It's certainly possible that by thinking about quantum algorithms, you're driven to think about different structures in number theory. I mean, Shor's algorithm doesn't work in the same way that classical factoring algorithms work. So you might think harder about structures in mathematics that you wouldn't have considered otherwise. And then you can make progress mathematically. There's a small set of results that have been established in classical computer science by thinking about problems in quantum computing. So certainly that's something that can happen, is you can think very hard about how to discover a quantum algorithm, for example, and accidentally discover a new classical algorithm. Something else that has happened is you can discover a new quantum algorithm, and then some classical person can come along and say, oh, that only beats the best algorithm we knew, but because now I can see what you did, now I can make a better classical algorithm. That famously happened with a problem called the 3-lin, where there was a nice quantum speedup by Eddie Fahey and Sam Gutman and Jeffrey Goldstone. And then the classical computer scientists kind of ganged up on them and improved the classical algorithms. And that, you have to remember, that's not a failure, right? That's a process of we're discovering better algorithms. And as quantum computing people, we prefer that that didn't happen. But, you know, as a human being, you just want to discover better ways of doing things. And if we can do it that way, then fine.
Yeah, so the breakthrough could be also from math or physics or not computing itself.
Yeah.
Do you work with optics mostly? I kind of read no, you're like looking at everything.
Well, I'm pretty agnostic. So we've certainly done calculations with optical quantum computers, and I mainly now really work with ion trap quantum computers. But we also do calculations on the IBM devices, which are superconducting. And so.
And just one more question, and I leave it to you because it just came up. So if tomorrow you discover something, you have a breakthrough since you are experimenting on everything, and you figure a way to break encryption or making it much more easy, what would you do? Because we also talk about the ethics of the quantum discoveries, and you know that there is so much now that's dependent on RSA and these systems, cryptographic systems, that if you do discover that tomorrow, what would you do?
Well, firstly, I think it's very unlikely I could discover something where I could factor, say, a 2048-bit key using the hardware that exists today. So if I was to do something like that, which I don't think is very likely, I think you have to publish it, because the way crypto systems evolve, you know, in practice you can't keep things secret, and it would be irresponsible not to publish it, because then, you know, some nefarious person could take it and do something unpleasant with it. But if you publish it, then everyone immediately has to stop using RSA, because they know it's a broken system. And as I just want to say it again, I think you should do that already. And so, yeah, I think you have to be open about these things. And I think that's the ethical commitment that is underneath science, is to you generate knowledge for the benefit of everybody. And, you know, unless you have an imminent belief that, you know, you would be able to break very large keys and some horrible thing would happen, but it would have to be a very specific threat that you would be worrying about to override that bigger sort of ethical commitment.
The damage though would be huge as well. So,
but that, to me, that's not clear, because people who are really worried about keeping their information secret are presumably already not using RSA. You know, if someone steals a lot of money from a credit card company, is that so disastrous? I mean, you know,
real damage versus virtual damage.
Yeah, I mean, there's economic consequences. There's crime, right, and theft and things like that. But, you know, compared to, say, loss of life and things of that nature, then...
Well, we don't know. I mean, there is so much that relies on that at this point that, I mean, I don't know, loss of lives, maybe, depending, you know, power grids, transportations, those kind of things, they do rely on this technology. So,
but, you know, there I would, again, do I believe that the power grid is secure because it uses RSA cryptography? Well, you know, there's a famous saying. You might actually interview the person who said this first, but I can't remember who the quote. But it's like the RSA is like a steel door on a grass hut. That, you know, I would much more worry that the power grid is vulnerable to the fact that, you know, it's not very well maintained, or you know, or there's somebody who could be bribed or something like this. So I would much more worry about, you know, the overall security. And again, that's, you know, that can only be improved if people are open about what they're doing, so that it can be widely, you know, critiqued and thought about. If companies are keeping secret what they're doing and nobody else outside the company knows how the power grid is actually secured, my guess would be they're doing that because they know it's not very well secured and they don't want to.
And even worse, if a company discovered this breakthrough and keep it secret, and they do whatever they want for years, right? So that also the other risk, ethical risk of like that someone wants to own it on the way to break encryption, whatever it is, an algorithm, math.
It's an interesting question to think how you would then do that in practice. There's always a question for the companies beyond all of the scientific, algorithmic, and hardware and practical questions. There's this economic question of then, okay, you can do all this stuff. How do you make $1 doing it? I mean, how do you make $1 from having broken RSA? Well, aren't you a thief? Aren't you stealing money? Wouldn't you, thieves already exist, that, the business model is vulnerable to getting caught, basically. And so, and it's true when, for example, if you take the Enigma machine in the Second World War, which is probably the most dramatic case where something that was believed to be totally secure was actually completely broken, it was a tremendous problem to decide when to use the intelligence because you would reveal the source. And then, if the Axis powers realized that Enigma was broken, they would presumably change their methods. But so I think it's economically breaking RSA is not the best business model.
Well, this is where we are going. Strangely enough.
You mentioned that we will learn as we have perhaps something an equivalent of a 128-bit key in factoring. We will learn from reaching that point so much that it will give us a better gauge. Sounds a bit like when we were first testing out the viability of RSA keys of various sizes. It sounds a bit like the kind of the public competition to make sure, and then the pace setting, which is one of the things that we started to look to NIST for, was when do we think we need to move? And we went from 1024 to 2048, right? And so is that a fair sense of what?
Yeah, absolutely.
Yeah. We'll get a pace set.
Yeah, and by the way, RSA did a great thing, right? They really had public competitions, and they did this in a public fashion to say these keys are broken. Yeah. They could have hidden it and said, "Oh no, 128 is still fine. Don't worry about it." But because they did it in this public fashion, it enhanced the security of the whole system. Yep. Yeah. And I think that's something I think is very interesting now. Is how do we start to, very clearly and openly communicate about progress in the field in various different settings, and I think RSA is one of them. About where we are, and I think having these competitions is a really great way of doing it.
We keep talking about RSA, and you seem to think that everyone should stop using it already. What's your take on elliptic curves?
So I have to have a disclaimer here, which is I'm not a cryptographer, so I don't work on this stuff.
Yeah.
But I do know that if you're totally convinced, we were just talking about Enigma. Mm-hmm. If you've ever been totally convinced that things are totally secure because your crypto system is so clever, you should worry.
You should stop using it.
I think that a certain amount of paranoia is natural. So in a way, we're struggling because it's very difficult to develop new quantum algorithms. Mm-hmm. It's really difficult. So we were a bit misled because Peter Shaw is such a genius that we had this, and I'm old enough to remember coming into the field close enough to that discovery, being quite naive and thinking, there's bound to be lots of quantum algorithms. It's going to be great. It's going to be like, being in a gold mine. And it's not really like that, right? And so I think that's an interesting thing to think about, where classically we haven't, we are, in a way, performing algorithms all the time in our lives. We have methods for doing things, and we think, this is a better route to drive to work. And quantumly, we don't have a lot of intuition about how quantum mechanics itself works. And so we don't really have a set of intuitive building blocks. And so we have to learn what those things are quite painfully. So I think it's very hard to think of quantum algorithms. And in that sense, that provides some protection. But again, maybe we'll suddenly get much better at it.
We are interviewing also people that actually are working on post-quantum cryptography. And everyone anyway mentioned NIST, but at the same time, they all, or not everyone, but mostly they say we don't know because
Right.
actually the computers are not here. So we have these ideas, we have these algorithms. Some
Yeah.
are already implemented actually, but we don't know because if the breakthrough is happening in a way that we didn't expect, all these efforts are
Yeah.
going to be useless. And do you see though some potential solutions in maybe creating new keys, or I don't know, you're a physicist, of course,
Yes.
but you also probably know that it's all about math. So maybe there is some more new ways to do it, or you're envisioning something. I don't know.
Well, certainly one of the things we worry about when you're thinking of simulating quantum systems with a quantum computer, you worry about problems that are too hard for quantum computers to solve. So that's certainly a place where, as we understand, where are the problems that are too hard for quantum computing, that's obviously a place where you would get ideas for post-quantum crypto systems. And so, I mainly think about the other case of trying to show, no, they're not too hard. But as we learn more, in all areas of the field and delineate that the set of things we can do on quantum computers, the set on classical computers, and the set that are too hard, then we'll have a better understanding of how to make post-quantum crypto systems.
It makes me think of the notion of like what might end up being called someone who is like quantum native. They have such an intuitive sense for the thing. That's what they learned. They first understood computers in terms of quantum algorithms, and that's the person to be really worried about, is someone who just thinks in these terms. They have an intuitive sense, like you said.
Yeah, but someone who's so unusual like that would perhaps not even be interested in mundane things like keeping secrets. They would be off in the higher realms worrying about something else, right?
Yeah, they were just,
so, oh no, but you can make all this money out of cracking RSA. So, oh no, I'm not interested in that.
Yeah, hard to get them engaged.
Yeah, actually, if I can ask, because we interviewed some physicists and they were saying that they started their career because of Peter Shor algorithm. Is also your case?
Well, at the time I got interested in quantum computing, Shor's algorithm was this, obviously huge achievement that had really taken the subject from something that a very small number of people were developing to suddenly there was a lot of influx of money. Compared to today, it looks like not so much money, but it was a lot then. And so yeah, it felt very exciting that you might be able to discover new algorithms. And as I said before, it turned out that there wasn't a Shor's algorithm under every rock. So yeah, I think that algorithm is really like a kind of guiding star. If you want to, even if you're not working on number theory or you're not working on cryptanalysis, the idea that you would like to do something like that, that's definitely a motivating.
Incredible, because all this technological development is all about breaking encryption. I mean, it's all about it seems like they started early on to today. I mean, there are many applications you can have with quantum computers, but still the driving force is breaking encryption. Sounds like that. It's incredible.
A friend of ours had a saying, what use case do you have for something other than solving the problem that it causes?
You have maybe a statement that you were thinking about quantum and ethics, or anything you wanted to say? There's the chance.
Yeah, I was thinking about the ethics. There's always a danger in science that you're going to discover something that will ultimately or even immediately be used for some terrible consequence. But that doesn't mean that you should stop, because you don't know what the ultimate consequences are going to be, good and bad. And if you start restricting science to say, well, we can't go in that direction because maybe such and such will happen, we can't go in that direction because we think this might happen, you also are going to miss out on all the positive impacts of the technology or the science or the understanding that you would have. And also, if somebody else creates that terrible outcome, whatever it may be, you're not going to be ready for it. You won't understand and you won't be able to predict what the likelihood of it is. So you sort of have to keep going. That's, as I said before, that's the ethical commitment that you have as a scientist, is you have to believe that knowing things is better than not knowing things. No matter that, of course, bad things can happen. And so, yeah, I think that's where I come down. So in what I do, I think the good outcomes of quantum computing have to do with really understanding the properties of matter in chemistry and in nuclear physics and in high energy physics and in any place where quantum mechanics plays an important role, but really understanding the structure and the properties of matter in a predictive way. So you could predict the properties of molecules accurately, and you could design new drugs ab initio without doing experiments or doing way, way fewer experiments. I think that vision of that world where we have that capability, whether it's achieved through quantum computing or through existing methods, that's a wonderful thing to think about. And if we suddenly stopped and said, oh, no, we can't think about this because we're scared of breaking RSA, I think we're missing out on too much.
Yeah, it's just because of this RSA problem. Otherwise, quantum computer would revolutionize science and many other things.
But you've got to say as well, we wouldn't be here if it wasn't for Shor's algorithm, because the thing about breaking RSA is it's such a beautiful, clean problem. Right? Anybody can understand the idea that you multiply two numbers together, you get another number. Going backwards is not as easy. The fact that RSA gave that simple problem such a huge, military and economic and political importance, and then the fact that one of the first important quantum algorithms broke it in such a beautiful way, that's created the field. And so all the other consequences of quantum computing are, side benefits of Shor's algorithm, I would say.
Well, still, even if it wasn't the cybersecurity question, there will be so much new computational power, and then we are going to face everything we are facing today with this big tech monopolizing, trying to own, trying to misuse it, right? Yeah. And so the ethical questions that are about this kind of like new power of quantum supremacy, right? I mean, this is the future, but I don't think it's going to end only with cybersecurity, unfortunately.
Yeah. And that doesn't apply only to quantum. I mean, these questions apply to all forms of technology, particularly to AI. Right. But, if you ask me the question, do we do a good job of making sure that outcomes of science are, ethically sound and societally positive? I would say no. We're not very good at that. Yeah. Right?
And these computers are going to be 1 million or 10 million times more powerful. So,
well, I would say I think we're so used to computers getting twice as fast or twice as powerful on some short time scale that we tend to think like that, as you said, in this is a million, my computer in my laptop now is 1 million times faster than the machine I used during my PhD or something like this. But I think it's the exciting thing for me about quantum computing is quantum computers might be able to do things that you just can't do at all classically. So it's not then a quantitative, we're faster or better or more accurate. It's just, we could never address this problem. We could never understand the, interior structure of a neutron star, for example, which is a real problem that we might be able to contribute to. And so one of the things we've been thinking about is taking an analogy from astronomy, where when you build a new telescope, the astronomers, of course, say, we are going to do all this wonderful science that we know will be there. We're going to improve this, and this is going to be better, and there's going to be more of these. And then they say, but because we're going to point this new telescope at the sky, and it's going to see things that nobody's ever seen before, we know we're going to discover a load of stuff that nobody's seen. And this is where we're going to discover it. So that idea of the discovery space, the idea that you can make discoveries with quantum computing of things you would not have seen with a classical computer, I think that's very exciting. And unfortunately, we don't have the long history of astronomy to back that up, to give examples. But I think that's what's more exciting to me. I'm more excited about that than I am worried about the negative outcomes.
Nice, thank you.